In example 4, we're going to start getting into half-life. And half-life is the amount it takes for something to decay to half of what it was starting with. So when we're talking about half-life, we're talking about a decay model. And the half-life is the amount of time it takes to go from whatever its initial amount is to half of that. So, for example, if I had a bag of M&Ms on my kitchen table, and there we started with an entire bag of M&Ms, and my kids walked by, in about 5 minutes, half of that bag would be gone. So the half-life of that bag of M&Ms would be 5 minutes. So, it says in example 4, a substance has a half-life of 2.62 minutes. So that means every 2.62 minutes, whatever amount remains is going to get cut in half. The initial amount of the substance was 58.4 grams. How many half-lives will pass before the substance decays to 7.3 grams? And then we got to figure out the total time of the decay. So, it says here, the initial amount, you start with 58.4 grams. This is the initial amount. In 2.62 minutes, this amount here is going to get cut in half. So in 2.62 minutes, if I take 58.4 and divide it by 2 on my calculator, I'm going to get that in 2.62 minutes, there's going to be 29.2 grams left because I cut 58.4 in half. Then in another 2.62 minutes, another 2.62 minutes passes, and you're going to take 29.2 and divide it by 2 again. It gets cut in half again. That would be 14.6 grams that would be left. Then, in another 2.62 minutes, 14.6 grams gets cut in half, and that would be the 7.3 grams. So from when you start to when we reach 7.3 grams, there were 3 half-lives. Each half-life took 2.62 minutes. So if I want to know the total time it took to go from 58.4 grams to 7.3 grams, that would be 3 half-lives, each worth 2.62 minutes. So the total time would be 3 times 2.62 minutes, which would give me 7.86 minutes. So it took a total of 7.86 minutes to go from 58.4 grams down to 7.3 grams. In example 5, it says a doctor prescribes 325 milligrams of a therapeutic drug that decays about 25% each hour. Write an exponential model representing the amount of drug remaining in the patient's system after T hours. Find the amount of drug that would remain in the patient's system after 3 hours. We're going to round to the nearest milligram. This is our starting amount. And then after time passes, it starts to decay in the bloodstream. So if we use this model, P is going to be our initial amount. And we have e to the power of r is our rate. Because it's decaying, we want to make sure we have a negative 0.25. Our rate is 25%, but it's decaying by 25%. So I'm going to put it as minus 0.25, and t is our independent variable. I leave that as t for time. So our model is this. This is our model. I plug in the time in hours, and it gives me how much in milligrams is left in the patient's bloodstream. So now that's our first part of the question, is to find the model. And the second part says find the amount of drug that would remain in the patient's system after 3 hours. So now we got to find what we get when we plug in 3. So this we'll put on the calculator. So I'm going to do 325 times e to the power of negative 0.25 times 3. And that would give me 153.5191296. And it says round to the nearest milligram. So this is going to be 154 milligrams when we round it to the nearest milligram. So after 3 hours, the patient starts with 325 milligrams, and then after 3 hours, he's left with 154 milligrams in the bloodstream. Example 6, it says the tumor is injected with 0.5 grams of iodine, which has a decay rate of 1.15% per day. Since this is decay, when I put this in for my rate, I want to make sure I put it in as a negative. It says write an exponential model representing the amount of iodine remaining in the tumor after T days. So since we're starting with 0.5 grams, that's going to be our value of P, our starting point. And our rate is going to be negative 0.0115. We've got to put it in decimal form, and I want to make sure I put a negative in front of it because it's decaying. And then I have my independent variable T for time, and T is in days. Find the amount of iodine that would remain in the tumor after 80 days. So now I'm going to plug in 80 for T. And I'm going to put that in the calculator and see what I get. I'm going to use my exponential function that's above my log button on my calculator. I'm going to make sure I use the negative button, not the minus button. And I'm going to put in e to the power of negative 0.0115 times 80. And that answer gives me 0.1992595,205. And this is in grams. The question says round to the nearest tenth of a gram, so that means one decimal place. So I'm going to round it to 0.2 grams as my final answer. Example 7 says, a scientist begins with 325 grams of radioactive substance after 220 minutes. The sample has decayed to 31 grams. To the nearest minute, what is the half-life of this substance? Okay, so now it's asking for the half-life. So now we're looking for the time it takes to decay to half of what it started with. So they're giving all the information that we need in here to do that. They're giving us 2 points here. They're giving us our initial value. So at time is 0, we've got 325. So this is going to be our value of P when we plug it into our equation. And they're also giving us a second value. When T is in minutes, at 220 minutes, it decays to 31 grams. So we've got 2 points here. What I want to do is plug this in to my equation so I can figure out what my R is. I need to figure out what my rate is so that I have a complete equation. Once I figure out what my R is, then I can plug in half of 325 for Y and solve for T to see how long it takes to get down to half of that. But I can't do that until I have my R. So first I solve for R. So think of this as my extra point. This is going to be my T, this is going to be my Y, and then this is my initial value P. I'm going to plug all that and solve for R. So I have 31 is equal to 325 e to the power of R times 220. So I knew what my P was, and then I used the extra point they gave me, which was the 220 and the 31, to plug in so I can find what my R is. So I'm looking for my variable that is in the exponent. And when we're solving for something that's in the exponent, I know that I have an exponential equation. And when I solve exponential equations, the first thing I want to do is isolate the exponential. So I want to get this part by itself, and then I can put it in log form. So the first thing I'm going to do is divide both sides by 325. So I have 31 over 325 is equal to e to the power of 220r. Now I don't want to put this in the calculator and get a decimal value yet. If I start rounding with my intermediate steps, it's going to throw my answer way off. So what I want to do is wait and round to the very end. So now I have my exponential isolated. I'm going to put this in log form. Since this is base e, I can use my natural log. So I have my natural log of e of 31 over 325. And that's equal to my exponent, which is 220r. And then I divide both sides by 220 to get what my r is. So when I divide both sides by 220 on my calculator, I'm going to do the natural log of 31 divided by 325. And then I'm going to take that answer and divide by 220. And it gives me negative 0.0106810.817. Now, I know that it should come out to be negative because this is a decay problem. If my r didn't come out to be negative, then I know I did something wrong. I got to go back and check. And I want to make sure I keep all of my digits so that I keep that accuracy. So, my formula with my r is y is equal to 325, which is my initial amount, e to the power of rt, and we said that r was negative 0.0106810.817 t. Now that we have our complete formula, we want to know how long it takes to get to half of 325. That was the question. How long does it take to decay to half of what we started with? Well, half of what we started with would be 162.5. So I'm going to start with 325. I want to end up with 162.5, and I want to solve for t. How long does it take for that to happen? Because we're looking for the half-life. So again, this is an exponential function. I'm solving for t, which is in the exponent. So I need to first divide both sides by 325. When I do that, I get 1/2 is equal to e to the negative 0.0106810.817 t. I know it's kind of a pain in the butt to keep all those digits, but you really need to make sure you keep that accuracy. Now I have my exponential isolated, so I can put it in log form. Since this is base e, I can write it as natural log of 1/2 is equal to negative 0.0106810.817 t. So that's my exponent. So I take my log, set it equal to my exponent, and then my last step is to divide by that big decimal value on both sides. So I have the natural log of 1/2 is divided by negative 0.0106810.817. I'm going to put that in on my calculator. That's going to give me 64.89, but the question says round it to the nearest minute. So we're going to write it down as 65 minutes because it said round to the nearest minute. Okay, the last example, example 8, it says the half-life of a radioactive substance is 13.1 hours. What is the hourly decay rate? So we need to figure out what the R is. So notice that they didn't tell us in the problem what we're starting with. We really actually don't need it because if I just say I'm starting generically with an amount called P, half of P would be half P. I don't even have to really know what that is. And since if I start with P and if I end up with half P, it's telling me it takes 13.1 hours to do that, I can plug in that 13.1 for t. So it takes 13.1 hours to go from p to half p. And now I can solve this for r to figure out what the hourly rate would be. So I don't even need to know what p is. Those disappear. I just divide both sides by p. So I'm left with 1/2 is equal to e to the power of 13.1r. And then I just solve this for r. Well, when I'm solving for something that's in the exponent, that's an exponential equation. So I need to isolate the exponential and put it in log form. This is already isolated, so I can go ahead and put it right in log form. Since it's base e, I can write this as natural log of 1/2 is equal to my exponent, which is 13.1r. So then to solve for r, I just have to divide both sides by 13.1. So in my calculator, I'm going to do natural log of 1/2 and then take that answer and divide by 13.1. When we do that, natural log of 1/2 divided by 13.1, we get an approximate value. It says round to 4 significant digits. So that would be minus 0.05291. There's my 4 significant digits. 1, 2, 3, 4. 0 doesn't count here. You just count these digits here. So my hourly rate as a decimal would be 0.05291. And this is correct that it's negative because it's decaying. It should be negative. If I want to put it as a decimal, then I would have to multiply by 100 and it would be 5.291%.